So, good afternoon again, all of you. We'll start the second sessions of today's event, and here Professor Stark will be talking about the drug developments application from the selectivity to targeted promiscuity. Okay, so this session, after these sessions, we'll be closing that the actual program, and then we'll go for the valedictory. So this is the last lecturing session. So please be very much attentive and clarify your doubts if you have any questions. So the last time of this visit of Professor Stark, he'll be talking. Hopefully, maybe in future again he'll be lecturing. So this is the last lecture. Thank you very much. This is all about this.
So thank you very much, and I must say it's really a big privilege and a great honor to having the starting lecture and also the ending lecture in this way. So thereby I really appreciate this in getting this on. And I would like to continue what we have started. So I have shown you that we have developed pitolisant and have pitolisant for narcolepsy, for obstructive sleep apnea, and that we are now in phase 3 clinical for Prader-Willi syndrome symptomatic, and that we are just a symptomatic treatment for Prader-Willi syndrome and so on. And that's really one reason we wanted to see if we can do something more. So we have understood the disease, we have understood the different possibilities, and there are some other possibilities. So what we would like to try if we get some additional effects of our H3 receptor antagonists, that they influence the effectivity, and that we have some multifactorial effects on these compounds, because also the disease is not only hypogonadism or just a cognitive impairment, it is much more. So it had different contribution at different aspects, and maybe we can hit more of the aspects, more of the symptomatic, maybe some of the causal treatment with the different approaches. So in most cases, like also with neurodegenerative disease, we have not only one cause, we have a number of causes, and they together make the disease in a real state for the different structure. So thereby, we are turning from one to another. And thereby, we are turning from selectivity, where we go on one target only. There are sometimes the people say multiple targeting, and then they have something like this. There's a magic shotgun where everything is hit, like the paints, where you hit everything in the structure in the different elements. But what we would like to do is a targeted promiscuity. We want to address more than one target, and we want to address the correct target in the different structures, and we want to design in the correct target, and we want to design out the target we do not want, the target that lead to unwanted side effects. But therefore, we must know not only the structure-activity relationship of target 1, also of target 2, also of target 3, bring them all together, and together with this, we must also know the off-target structure, in which way, what should be avoided in many cases, and so on. So then getting more and more complexity into the different compounds, in the different classes in this way. What we have seen here, just a short introduction or just short explanation, what you see here, that one compound was described as a G9A inhibitor. G9A is a histone inhibitor. Histone is an element which is on the folding of your DNA structure essential. So you may have known from demethylases or deacetylases, histone deacetylases, which then leads to the unfolding of the structure. And this is a very specific histone modificator, histone methylator. It is a leucine-based histone methylator, and thereby you make some epigenetic reading of this. Epigenetic means that you do not change the gene, but you change the probability of getting this gene read or getting into further reading possibilities with other structures and so on. So that means even if you look at twins, they have, many twins have the same genome or more or less the same genome, but they look totally different. And also we have already learned that we have only 1% different genome, but we look totally different. But our genome is very similar. But our epigenetic, the reading of the genome, that is quite different in this way. And there, some authors describe this UNC compound here, and this UNC compound here is a G9A inhibitor, and it was described as a causal inhibitor of Prader-Willi syndrome symptomatic. So by epigenetic profiling, they're changing then in the mouse model, the Prader-Willi mouse into a more healthy mouse with this epigenetic reading. So thereby this was a histone H3 structure. In fact, this is really histone H3, and we wanted to combine histone H3 with histamine H3. So different H3s combination in this way. That's why I was also interested, because it's at least for my kind, funny literature. This H3 with different meanings in this way. Yeah. And you see here also once more with the structural element, we do have this amino structure, the propylamine, the oxy structure, and then the phenyl moiety in this way. So we already saw that there are some elements which could be combined to the different structure. And then we looked for other described G9A inhibitors, and we found this A366. In fact, A366 this A is for Abbott. So Abbott designed this compound, described it already as a G9A inhibitor, and then we bought this compound because it's commercially available, and then we tried to design this compound really further on, or to look if this is really possible, that with this substitution pattern, do we have a H3 receptor inhibitor or not, or could it combine or not in this way? So we make the profiling of our compound, because not so many data on G proteins were available, only on G9A on the genetic reading and things like this. What we did also for this compound, that we looked on lipophilicity, size, polarity, solubility, and then also on some lipophilicity in the unsaturation fraction in this way, because this compound does not look in our eyes too much drug likeness, or there could not be so much variations. Whereas with this compound, we thought that there will be good variations if it's needed for further structural elements in this way. So thereby, these different structures do not fulfill all this criteria. Only this compound here fulfills this criteria, and then we are going on. We measured this compound also by this biotool, drug likeness tools, and so on. And there, during this week, I received a message that one colleague of mine has published a paper in British Journal of Pharmacology and describing their different biotools. So where you can calculate different properties and so on. So I can highly recommend this by Marcel Bermudez. It is in the British Journal of Pharmacology, just recently appeared. It's just an ASAP print, so not originally thing, but it's an open access and can be clearly accessed in the different ways. And here we also benchmark different lipophilicity parameters and so on. And this small compound had all drug likeness parameters calculated by the open source Swiss ATME in this way for the different structures in this way. So it was clearly useful for different structural elements. And then we checked the histamine H3 receptor antagonist activity in these properties, antagonist activity in a luciferase gene reporter assay, and we recognize that this compound is really potent H3 receptor antagonist in combination with the G9A inhibition. I have only a few slides on this story, but I would like to demonstrate this, that is A366 from Abbott. They have nanomolar activity at the G9A, 2.5 nanomolar, and about 70 nanomolar at the H3 receptor. So quite useful, and a balanced activity at the different structural elements, and that was for the human as well as for the rat structure, and good selectivity concerning other histamine receptor, other dopamine receptor. So it's a compound worth further developing in the different structure. And even Abbott was not aware of the drug likeness for the H3 receptor of this compound, because they have not tested this. So that's really a good possibility in which way this is really acting. And then we have pitolisant on the symptomatic effect, and we would like to combine this with the A366 or with the G9A inhibition to go for the epigenetic reading. With the tree here, it's just the symbol that we are going to the roots with the epigenetic modification, and we are going to the leaves to make some symptomatic treatment in this way and to find many possibilities in which way they can work together in the different ways. So thereby, these A366 is already a nice compound to have, and we see that there are also some other epigenetic modifications which we have measured in this way. So that was then seen as a new property of the structure. But it's also, before this, G9A, or the A366, was taken as a chemical probe for G9A. So with our screening, we could show that it's maybe not the best chemical probe, because it's also binding to the histamine A3 receptor, and thereby the properties of the chemical probe may be limited in some studies, as you see also some other effects. So thereby, with additional screening, additional learning, you see some of the additional structures in this way. And thereby, the A36 is one of our starting materials now for making combined histamine A3 receptor and histone A3 methyltransferase inhibitors for making a combinatorial chemistry, multi-drug combination in this way, in one compound having multiple properties in this way. And thereby hopefully get into a new treatment for Prader-Willi syndrome children to get both things combined into this aspect. Just to show that we are really working on different aspects for the different properties in the way. And I missed with my last lecture my co-workers in the different fields. I mentioned several times the co-workers from Bioprojet and in ZERM, Robin Ganellin from UCL, but also here Lara Pullen made the Chion Foundation, Maria Piccone made the Trend community, my own co-workers, who started this project in Frankfurt and continued then in Düsseldorf in this way, and also many support from European Union in the different apartment here in this way for the different structural elements in this way. And you see here, this was my working group in Frankfurt, this is my working group in Düsseldorf at that time for the structure. What I would like to show here is from selectivity to promiscuity, to targeted promiscuity, and that is our basic round where we stay so long for the same structure because we have developed some very selective compounds. We have developed some very selective compounds which we even went into clinic. So we knew in which way what is missing with the compound, that they are not optimal, and we know many other compounds in which way they can be optimized by a combination, by some add-on. Yeah? And thereby, we would like to address different targets simultaneously in this way. And there's different possibilities with addressing different targets simultaneously. For example, you can take a cocktail. Yeah? So you can 3 drugs, and then add these 3 drugs, and then you add all of these 3 elements together in this way. This has the problem that in most cases you have to take a large amount of each of them of the drugs, that they have different pharmacokinetics. One lasts maybe for 1 hour, the other lasts for 6 hours, so when to take what, when and so on. The distribution is different, maybe they have additional interaction and so on. So it's always increasing all the difficulties if you take some cocktails. The more drugs you take, the more problems you get even with this problem, thereby pharmacokinetic, compliance, drug interactions, efficacies and so on, they are quite often hindered in this way. And thereby we are trying to put 3 properties into one molecule. And I know one important chemist who said chemical synthesis is not for synthesis. It's for the synthesis of properties in molecules. And that's really what we are doing. We would like to include properties in our molecules and especially design properties for our compound we're looking for in this way. This can be done in different ways. You already saw that there are some cleavable ways in which pharmacophore 1 and the other pharmacophore could be combined by a cleavable chain, and then they are released at a certain scale, and then you give 1 compound, but at the end you have to investigate 2 compounds or 3 compounds because the uncleaved structure, cleave partner 1, cleave partner 2, so that's also quite a lot of different things you have to investigate. Whereas when they are just connected by a chain, then you only have 1 compound in this way, but the chain must be acceptable, quite often get into longer molecules. Or you can some additive or at best integrative compounds where you have some overlapping of the pharmacophoric elements in this way. Can you already see what is the main advantage for the integrative compounds in comparison to all of the other compounds? Lower molecular weight. Yeah? If you combine pharmacophoric elements, you're not combining two molecules, but you're overlapping in the structure, and thereby you have lower molecular weight, and you have more possibilities for variations and for step-by-step structures in this way. Yeah? As you've seen with many of the other structures here, that there are many possibilities in which way this is really done. So multi-targeting ligands is one of our main purpose for the last decade or something like this, and there is multiple targeting there that you can linking, fusing, or merging. You can name it differently in the different purposes. What is then the main difference is, do both targets need the same affinity? Or does one target need a higher affinity than the other one? So do I need a target balancing, or could be one target less than the other one? Maybe you have some overexpression of the receptor, or you have higher affinity of the ligand. So what is the disease state you're really treating on? And I must say, in fact, in many cases we do not know. So when you have cocaine abuse, what is your regulation of dopaminergic receptor? What is your regulation of dopaminergic receptor with Parkinson's state? At which Parkinson's state, and so on. So that's really difficult to see in the human, and thereby this correct balancing is quite difficult to see and to predict. Yeah? Thereby, it strongly depends on the disease model you are working on, and then you can work for the different structure. Yeah? And you see here, lowering molecular weight, increasing drug likeliness, all speaks for the merging, for the integrative approach for the different structures in this way. Yeah? So when you are successful, I always go for the success, and then we make some changes for the different structures, and thereby this P2 design is still our main structure for the different elements. And then we saw here that Parkinson was tested, showed some beneficial effects, but not really enough to go into clinics. So we looked for other approaches in which way we can approach Parkinson's disease in this way. And an important point for addressing Parkinson's disease are monoamine oxidase B inhibitors. So there are two different monoamine oxidase, and the monoamine oxidase B is mostly transforming dopamine, but also other phenylethylamines, whereas A is responsible for serotonin and epinephrine and so on. So it should have a relative selectivity for MAO-B, and then this could be done. And you can see here rasagiline, deprenyl, or safinamide. There are 3 different compounds are marketed as MAO-B inhibitors for Parkinson's disease treatment in this way. You clearly see, hopefully, that they are 2 different classes of compounds, whereas here you have the triple bound here in the different structure for the secondary amine. These are irreversible inhibitors because they react with the MAO-B at the FDA, the flavine monooxygenase stage on the interaction, and they are interacting irreversible. Whereas here, this structure is a derivative of the amino acid you see, and this is a reversible inhibitor, a little bit lower potency, but has also some additional potassium channel activity in this way. So, sodium channel activity in this way. So they do have some additional effects on depression, mostly on Parkinson, but they are really in this way. And then we were looking in which way we can combine one to the other element in this way, and then get into the different structure. This was done already with us and also with other groups. So there were already combination of the H3 receptor with other targets in this way. And you see here, there were combination with other G protein coupled receptor. There were combination with other enzymes, histamine methyltransferase, acetylcholine and butyrylcholine esterase. In fact, also by us. There were combination by transporters, mostly by Pfizer and by J&J, Johnson & Johnson. And we also made some signaling overlapping with NO signaling. And now we wanted to do some enzyme coupling to MAO-A, but mostly to MAO-B in this way to get into new compounds into multi-targeting drug design for this ligand and so on. So that's what we are going on. So we have our clear structure, we have some elements, and now we can see here, you have here this aromatic moiety, here the aromatic moiety, here the aromatic moiety, and then we can combine these different structures. Our main point going for this, that we were profiling ciproxifan furthermore. And ciproxifan, which I also explained as a chemical probe before, thereby I needed this 2 hours explanation before to come to this story in this way. You see, here we explained that ciproxifan is a moderate inhibitor of monoamine oxidase B and also slightly to monoamine oxidase A. So we already saw that some of the H3 receptor antagonists, they could inhibit simultaneously MAO A and even better MAO B for a certain extent. So that we took as a very nice starting point, that further compounds were developed, and then we looked here for the non-imazole compound, and here even the MAO B preference was slightly enhanced. There was a 100-fold selectivity between these receptors, and here in the red dot you see that's even much larger affine for the histamine H3 receptor. So we have about micromolar affinity for the MAO B, and we have nanomolar affinity for histamine H3 receptor. Maybe not the best balance, because when we look for the MAO B inhibition, most of the other irreversible inhibitors are also in the nanomolar, maybe 2 to 3-digit nanomolar concentration range, but not really in the micromolar concentration range. So there must be some further improvements where we go better into the balanced activity we are having here for the histamine H3 receptor, for the structure and for the structural elements in this way. So we had some previous investigations where we only prepared some MAO inhibitors. So our previous investigation on MAO inhibitors were looking for these ketones in this way. And you see here, there are some similarity to what have been observed with our ciproxifan. And here we made some further variation with a double bound on this side. And even these compounds have then MAO B in a nanomolar activity for 9.2, or here 3 nanomolar activity, and these compounds were even more promising because they exhibited higher selectivity for MAO A. So we're not only working on H3 always, we also have other enzymes where we modulate or make some other modifications and so on, but in most cases then we try to optimize our structures, and here is our optimization strategy to bring 2 different strategies together in the different approaches here for the way. And then we took these examples, and then we added these compounds here for different structural elements, and then added these compounds for different possibilities for new potent histamine H3 receptor antagonists with some additional properties for MAO B, maybe for MAO B in this way. Yeah? And you see here, since this is our real research, I'm demonstrating here my first slide for synthesis, really, or in fact, my second slide for synthesis, because this is organic synthesis, and you can read this everywhere. So the main point here is for medicine chemistry, in which you go on for this, but you see it's easy combination for different possibilities for ether formation, for condensation reaction at different points. So to my mind, classical chemistry, which nearly goes on for the different points, for the different structure. What was seen then with some of these compounds, that some of these compounds had some alpha-beta unsaturated ketone structural elements here. Like you see here, alpha-beta unsaturated ketone element in the structure, possible Michael acceptor, potential pain inhibitor, pan-assay interfering inhibitor in this way. And then we tested this compound for nucleophilic properties. Normally you test this compound by the addition of glutathione, because that is the regular detoxification the body takes. Yeah? So glutathione makes some detoxification and makes some thioether bond, and then glutathione is then measuring here. What we were taking then, we were taking acetylcysteine as an easy, versatile, and also cheap substitute of glutathione, because it also contains the thiol moiety, and then we checked in which way this acetylcysteine is adding to the buffer medium. And we could check it on different purposes. So you can check it by NMR studies, in which way this is added, or we were taking our mass spectrometry, which then calculating the different masses that have been explained, and that could be easily done by different procedures. So you can easily check your compounds for this chemical reactivity in this way, and thereby for pain's possibility. And fortunately, this compound were really stable because of the both aromatic structures here. They were more stable than we expected in this way. So we do not have this problem for this way, but it must be checked. Yeah? So that's quite important for the different structure. And then we had a number of different compounds, checked them for MAO A and MAO B screening, and our we have limited resources in all of these aspects, and thereby we took our resources and then we made our screening at 10 micromolar. So we tested, we do not determine all of the IC50 value for all the compounds, but we make a limitation. So compounds which have at a 10 micromolar, a lower inhibition than 75% of this, were not considered to be really useful for our further investigation. And a few compounds really break this border, and then these compounds were really taken for real investigation, for determining of IC50 value, for determining of selectivity, for determining also another aspect. So by that way, we had a triple determination of a one-point structure, one-point biochemical activity, and this reduces our cost for the screening and so on. Yeah, because here we have one-point screening in triplicate to be sure from the statistic evaluation on this, but then we make 7 or 8 points also in triplicate for the IC50 determination and so on. So that was much easier here to get this 70.5 cutoff inhibition for the one-point screening with the different compounds. What was also seen that there are also some compounds which do not display selectivity, but most of our compounds really display some good selectivity, especially the ones with a higher activity. They were quite promising in this activity range and went on for the different structures. So then we made this exact inhibition, and then we showed all of the different test concentrations. With some, we get even to lower test concentration, to 2 or to 5 micromolar, and to see then our compounds. And we compared this to the histamine E3 receptor affinity, and they were between 6,000 and 2 nanomolar. So wide range for the different compounds in this way. And so we also have to look here for the different compounds in this way. Then we saw here with this compound, we saw a high selectivity range, good activity, and this was also for the enzyme activity relatively highly active. After different time scales, we got a good inhibition of the structures, and this was also true with the other structures we have here. But why, once more my question, why maybe 3D is more promising than 3E or 3F in this way? Once more, lower molecular weight. Yeah? You see, here we have this benzylic structure, mostly concerned with other elements, so other reactivity, radical reactivity, and here we have just fluorination. So these compounds may be a little bit better for safety reasons in our drug environment. And that's, you can check with the different compounds, or you develop a view that you really be aware of the problems, of the potential problem of these compounds, and then you focus just on this compound. Maybe it's not the best from the affinity, but from the prospect, it seems to be much better than the other one. Yeah? And this is maybe by increase of lipophilicity that you get this additional screening of the different structures in this way. Yeah? So we screened this compound, we screened them on the H3 receptor, we screened this compound, and we screened them on MAO A and MAO B. And then you see here that we have 2.2 nanomolar for the H3, and 500 nanomolar for MAO B, and 9,000 for MAO A. So getting better into the direction, but still not really there where we want to go. Or with this compound, 6.5 nanomolar for H3, 260 for MAO B, and over 10,000 really for MAO A. A little bit better, you see, from selectivity reason, but also for molecular weight, maybe not the best. We are going for the different structure. So there, these interknown derivatives were quite useful. We're combining two pharmacophores. We had reversible MAO-B binding, which is good. We had moderate drug likeliness, but in total, we were not really sure if these compounds could really be brought to market or even to human trials and even to animal trials and so far, because they were so big, they had so much possibilities for metabolic pathways and so on. So it was not our main purpose. We were going for the different structures. Yeah? So there were different possibilities in which way we can go for the different elements. And then we had another partner where we're going, and this partner was going for some indole derivative, and these indole derivatives were having here the MAO-B inhibition and here acetylcholine inhibition in this way. So he was also working on this compound, and this ASS234 was also a multiple targeting compound, and was a compound combining MAO-A inhibition and acetylcholine inhibition in this way. Yeah? And when we saw this compound, you clearly see that there are some stronger variations here, but nevertheless there were some possibilities to this ciproxifan analog, where we have the non-imidazole compound with the different structures. And we already saw from our previous structure-activity relationship that we have this Lego brick system to bring up our compound system. Yeah? And then maybe we can take this element and then modify these elements here and getting more into these details here and making then a new compound for the different structures elements. So thereby, it was our motive that we would like to have the H3 receptor activity, that we would like to have the MAO-B inhibitory activity, and at best we would also have the acetylcholine esterase inhibition and the butyrylcholine esterase inhibition, which is combined here with this structure in this way. So there are at least 4 targets here we were like to look for, or even 5 targets when we take the butyrylcholine esterase also as a potential outside in this way. So we get rid of the 2 targets simultaneously. We want to address 5 targets simultaneously. Yes, you see, very sporty in this way. But if you're not trying for the best, maybe you're not getting there in this way for getting these compounds. In fact, then we made a couple of different compounds where we have this indole structure and we have this benzylic-like structural element for the ASS compound, and we made the combination, and with a small number of compounds, in fact, even we were less than 6 or 7 compounds we made in the series, and then one of these compounds was our initial structure with this element here, and this is later on called contilizant, and we have 11 nanomolar activity for the histamine H3 receptor. And I will disclose a little bit more what we have here. It was a straightforward synthesis when you have this element here. Yeah? This is really the crucial element. It could be here amidated and then reduced, and then combined with this propagulamine, and at the last step you make the ether synthesis here, and then you got here directly into this compound in this way. Yeah? I think the alkylation is a little bit tricky at the final step, but nevertheless all of the other steps are quite working fine for this approach and so on. And it turned out that this compound was not only active for the histamine H3 receptor. We made some modeling here. We could also show that the modeling for the MAO-B with this element here also showed some elements of irreversible binding moieties. Mostly even better here for MAO-B in this way. So slight MAO-A, better with MAO-B, and also for the acetylcholine esterase inhibition, this compound was nice. But this also included that we have not only one molecular modeling, that we have at least 4 or 5 molecular modeling procedures, because different enzymes, different GPCRs and so on, so that workload tremendously increases with the targets you're working on in this way. So that's also must be sure in this way. So then we made this compound, this was our starting compound, this contilizant, and this compound without the propagule moiety here, this MTL compound, and you see with this compound, we did not get any MAO A or MAO B activity. With contilizant, we did not exactly reach this activity, but minus log IC50 values about 7.1 were really sufficient already for the structure, but you also see that there are different time points, 0 and 30 minutes. So with the inhibition of the enzymes, you're not really going for IC50 value. Very often you go for Km values and so on. And this gets even more complicated when you go for irreversible binding for enzymes, because then your enzyme stops working, and then the IC50 is not the determining effect, but the duration of the compound on the enzyme really, or in which way the enzyme can be rebuilt in the different structure, that are really then the important point in this way. So not always is IC50 the main point in this way, and thereby we took this contilizant even for longer testing, and then we see even with longer testing a slightly reduction in the effectivity, but nevertheless quite good for the different targets. So when we had our starting compound, this compound we had low activity for the histamine H3 receptor, which is here in this web, in the spider web declaration, where we have the H3 acetylcholine, butyryl, MAO A, so MAO A and MAO B activity, and then calculated as pKa value or a PIC50 value. So then the longer it is here, the higher the affinity here. And this compound has higher affinity for MAO A than for MAO B, and has moderate affinity to H3. And you see the targets for acetylcholine and butyrylcholine were not really addressed with this compound. So it was more or less a MAO A inhibitor in the different structures. And then we had here our contilizant, and you can see here with the red sign here that we have strongly increased the H3 activity, slightly increased the acetylcholine activity. We maintain more or less with the MAO B, with the butyrylcholine esterase activity, slight increase of the MAO B, but strongly decrease of the MAO A activity. So we increase our targets and we decrease our off targets. That means design in and design off ours. So this compound is much more favorable and has a lower molecular weight, has a lower lipophilicity and so on, so much more favorable activity in this way. And the same is true if we are not looking for the desired target, so this 5 desired target, we look for other dopamine receptor or histamine receptor subtypes. Even with these other receptor subtypes which are unwanted, we do not have any real effect on these compounds. So it was a nice example of designing in structures and designing off the corresponding element. Because very often when you change your lead structure and you make something in addition to this, then you get some additional activity at some other partners in this way. So that's, in many cases, you have some histamine H1 receptor activity and then get some sleepiness and so on. So that's really the main problems we are having here. And then this contilizant was further characterized, and we also took the antioxidative level because we have some benzylic, or in the indole structure, some benzylic-like elements in this way. So we have some radical scavenging activity. And here with the red bars, you see the radical scavenging activity of contilizant in comparison to melatonin or the previous compounds. And in most cases, we were better, or in all cases, we were better than the AS compound. But in most cases, even here with the rotenone model here, we got even better with our compound here than the melatonin, another target which is on the protective effect. So even with the neuroprotective effect, antioxidative or neurodegenerative, prevention of neurodegenerative effects, we were much better than our starting compound and showed a clear improvement. And we are here also above 60% with most of these areas in this way. With the radical scavenging effect, we also take this oxygen general radical absorbance capacity effect, normally only called ORAC assay. Yeah? And with the ORAC assay, you're testing ferulic acid, and then you test your own compound in comparison to ferulic acid, in which way they can inhibit then this oxidation procedure in this way. And then you see here with different concentration of a compound, we could concentration dependent inhibit this oxidation, and thereby have also directly an antioxidant effect of this compound. So in addition to the neuroprotective effect, we have the antioxidant effect, and I must say the antioxidant effect may be even more prominent because oxidation and oxidative processes may be one of the reasons of Parkinson's disease. So that would be maybe disease-modifying compounds when they get into more structure in this way. Yeah? And then you have this comparison, 3.74 to 3.59, so even slightly more potent than this reference compounds, our chemical probe, ferulic acid, for the antioxidative effect. Then we went into further studies into some animal trials, and there we looked at models of learning and memory, and also on lipopolysaccharide. So the lipopolysaccharide, the beta structures are then also connected to Alzheimer or Parkinson in this way. And then we made some novel object recognition. So the mice are placed here, and then they are exploring this chamber, and then they are taking out. This is done several times, and then you are measuring the time needed there. And then you put the mice into the same chamber, but you have exchanged one object here, and then the mice is very eager to learn the new object, and then they spend much more time at the new object than at the old object. And then you can look in which way this new object recognition really reflects some time in this way, and thereby calculate the learning and memory, because it learned the old factor and will explore the new factor in this way. So thereby you're getting this calculated in the different ways. And there you see also here with contilizant, this exploring factor and the learning and memory was strongly improved with this different structure. And you can also once more see we need some lipopolysaccharide to deteriorate their learning. So they have a impaired learning behavior by introduction of lipopolysaccharides. And then we can further restore, improve the learning behavior by the addition of contilizant, and much better to a significant way than with the other compound into this area for the structure. Yeah? So you see that we have here a good affinity at the histamine E3 receptor, moderate activity at MAO-A, and good activity at MAO-B. And it's also effective to have moderate activity at MAO-A, because when MAO-B is fully inhibited, then then the enzyme makes a shift. Then MAO-B takes also, MAO-A takes also dopamine and other structure. So you must have a moderate inhibition of MAO-A also because of the relative selectivity of the structure. We have a moderate activity at acetylcholinesterase and a very moderate at butyrylcholinesterase. So most of our targets here about 6 or higher 6 with the log Ki values, and we have designed out all of the other structures here with the different structures. We could also show that these are, we inhibit mitochondrial intoxication by radical oxygen species, these ROS species. We could have the antioxidant effect, we have the amyloid effect, and what is even then most important, that we have a pro-cognitive effect in mice in vivo. So we could apply this compound, and it's well absorbed, well distributed, and in brain it shows these pro-cognitive effect in vivo I showed with the learning behavior for the new object recognition in this way. So then we looked for different targets and then looked for the balancing in this way. So this is my summary for the multiple targeting approaches, where we have 5 different targets simultaneously. 5 different targets means that you address 5 targets at the same moment, and you address the other 100 targets not really at the same moment. So only you have 5 players which are really important in this way, and you design off the non-players, the unwanted side effects in this way, which is as important as to address the original targets in this way. Yeah? So that's quite important for the different structural elements in this way. All of them are in the brain, so we have to also address the pharmacokinetics and to distribution into the different areas. And then we can measure affinity, efficacy, selectivity, yeah? But what we cannot measure is this in the disease state. How many receptors are expressed? In which way these receptors are coupled to the signaling mechanism? And what is the receptor density, the disease state, and so on? And where is the distribution within the brain? We have different brain areas with different constitution, limbic areas, cortex, and so on. So the brain is not one organ. It's a summary of many organs in this way, and they have different compartments and so on. So we do not really know what's happening there. And since we are not able to predict this, we have to test them in animal screenings and so on. And here, we do not know what is the correct balance for the different activity, for the different structural elements. To my personal point of view, you can see these different targets as instruments. Yeah? You see, yesterday I showed you some fine arts. Now I show you some music in this way. And this is comparable to have some music. And with the music, you have some balancing. Some instruments are playing loud, some are not so loud. And then when you have these instruments at a good balancing activity, then you have a good music in this way. And not all instruments are playing at the same time. Some instruments are playing here for some purposes. You can combine this to make it more happening. You can just play your violin, yeah, and then it's also already fine. But you're taking then other violins and making some trumpets into this. It's even better for sound in this way. The same is then with the multiple targeting. One target may be enough. But when you add another target, it may be better. And when you then add a couple of different targets which are playing together, making the same music, then it's really fine. If everybody is playing its own music, you have a great chaos. Yeah? That's why I have, when my children play some music, let's have something you do not take for too long in this way. But here, we're having here this concert with a few instruments, and at the end you have to add on different aspects in this way, and you see this concert and playing in a certain round. And this is what I would like that you agree with the multiple targeting, that multiple targeting is nice and a fine address, but only if the instruments are playing together. And if they are playing in harmony for the different instruments, and then giving you a good playing round, a good music for all of the different instruments and going for the different structures. And with this, I would like to stop here and to thank you for your kind attention. And this is my last slide for the multiple targeting approach in this way. Thank you for your kind attention. Thank you. Any questions? Or too tired? Which I clearly understand after 1 week.
Question, please.
Sir, I don't have any question, but I am very inspired and motivated by your studies, sir.
Thank you very much.
Thank you, sir. Recently, I am not feeling well. That's why I am not able to attend all the lectures. But I joined through the YouTube links. So your research is very. I am working on anti-cancer activity. Yeah. So it is ignited my mind for research further. Thank you, sir.
Thank you. Maybe what I say, I just presented our research mainly focused on the histamine H3 receptor ligand and connected to this, because by that way I do not have to introduce all of the sphingolipids or the dopaminergic pathway, which we are also working on, or other structural elements, but just making for 1 week really a little bit better to oversee what we are doing or what can be done, or where are the problems in medicinal chemistry, and where are also some solutions. And my personal point of view is that you take into account creativity in this way. And I feel the better you go into medicinal chemistry, into drug design, the better you're going into creativity. Yeah, so that's not really, it is good handwork for chemistry, it's very good knowledge in this way, but then what I described yesterday with the pattern recognition and so on, that there are some other possibilities in which way you can put this into a new aspect into this way, and to get new and innovative approaches, it's very helpful to know the old ones. So the better your knowledge on the different purposes is, the better you can get into new approaches for the different aspects. And thereby, with a good kind of knowledge, you can be really innovative, non-obvious, making new patents, making new drugs, hopefully. Yeah? But it takes a lot of time, work, and also sometimes a little bit of luck.
Any more questions?
Thank you so much, sir, for your wonderful lecture. Sir, I want to ask, multi-targeting drug designing, is it like a dual targeting or dual action of one single drug?
Yeah. There are, with these drugs, there are multiple actions. Yeah.
You are saying the multi-targeting drug designing.
Yeah.
But I am saying the multi-targeting drug designing, through multi-targeting drug designing, we can design the dual targeting.
Yes.
Like if you want to control the hypertension, you have to 4 types of target. I guess 2 of them is AT, angiotensin, or AC.
Yeah.
So one drug can simultaneously act on these 2 targets.
Yes.
Is this drug designing method, multi-targeting drug designing method, can we do this?
Yeah. From the molecular aspects, yeah?
Yes.
When you have one receptor, then this can only act with one molecule and can only interact with one of the interaction site. When you have the other target, then it interacts with another molecule, but also with the same structure of the molecule, but one molecule interacts only with one of these receptors at a time. Because that just means receptor occupancy by your compound. There are also some possibilities in which way you have 2 targets nearby, and then you can make 2 binding sites, and then you have dual targeting within one structure, and you have the combination of this. But with these approaches I have, because the H3 receptor is on the cell membrane, the monoamine oxidase is on the mitochondrial membrane, so they are not coming together. So these drugs, they act on different positions of the cells, and they do not act together. What you're saying, when you have, for example, some dimerization of the structure, have 2 different binding points, then you would increase the binding if you have both targets addressed simultaneously. But to my mind, it's not multiple targeting, it's multiple ligand recognition, because you address the same target, but on different binding sites and so on. That's also multiple binding, but on the same target. And thereby you increase the probability, binding affinity.
Is there any way we can do the dual action of one single drug?
If you know both binding properties and you know the distancing of both binding properties, you can design some compounds like this. So from theory, it is possible. We tried this on the receptor dimerization H3 and dopamine, and we were not successful to address them simultaneously. So there we saw that they are in the membrane, and then we localized the structure, and then we made some compound in which way this pharmacophore is connected to this pharmacophore, but the distance was so long that it took all the mini polyethylene glycol units into this way, and even this was not enough because we were going through the membrane. And what is mostly thought that you have to go outside the membrane and then inside the membrane, but that gives even more flexibility for the different compounds. But we were not successful on this. Some compounds are described in the morphine receptor, in the opioid receptor subtypes, which should be successful. But these compounds are so large then, or because of the linker length, that there may be some single compound may be more useful instead of the the combination. Because if you block them on the one side and block the same on the other side, maybe then you have some additive or synergistic effect for this structure. But so multiple targeting makes sense, but not always into one compound. This structure, yeah? From especially when you go for chemical probes or things like this.
Okay.
Yeah?
Thank you, sir.
Sorry for not getting one answer. This is the solution for this.
Good afternoon, sir.
Yeah.
How does the proxiform across the blood-brain barrier and central nervous system activity?
This compound has just a poor basicity from the imidazole moiety and has no acidic element, so it's in a neutral form within the blood, and thereby it's quite lipophilic, and by passive diffusion it crosses the blood-brain barrier. And then it's a little bit, it has a protein binding capacity in this way, which is described, but in the brain it is more stuck to the brain protein and brain lipids in this way, and thereby this compound has a higher concentration in the brain than in the blood after some time. After absorption, it has a higher distribution in the brain than in the blood, which makes it even more comfortable for the things, because we have a low receptor expression in the periphery from the H3 receptor, but there are some H3 receptor. And normally we do not address these receptors because all of our compounds belong to the similar classes of the imidazole and non-imidazole classes, and many of them, they have a higher distribution in the brain than in the plasma, and thereby they get more effective in CNS diseases than in peripheral diseases. Yeah? Which is totally different when we work on the histamine H4 receptor. There we stuck mostly for the periphery, and we want to have more hydrophilic compounds which are less distributed in the brain. The H4 receptor is a peripheral receptor, not a central receptor. Good. Thank you.
Sir, in last lecture, Ghosh sir has said that for anti-cancer activity, the drug will act as a therapeutic, also can give the images of the environments. So in that aspect, multi-targeting drug design is applied for there?
Yes, for sure. The main problem, if you have your real cancer target,
Yes.
then you can address this target. But the target is not cancer; it's just some protein, some protein molecule you have to address, and there you must see what properties these compounds have in the cell. And it would, when you address these cell lines, for example, kinases or other proliferatory enzymes, they are helpful. But you must also be aware that this is not there, or not in this concentration there, in the healthy cells. So you do not want to kill all cells, you want to kill only the cancer cells.
Yes.
So thereby you must have some selectivity, and that is important by your target selection.
Yes,
So you can kill a lot of cells, this is not the problem. Yeah? Many drugs are toxic, but then you have to decide what is the acceptable range that I kill healthy cells instead of cancer cells. And that's, you see the risk-benefit ratio goes always more and more into benefit and less risk. Yeah? And with the classical alkylation agents, at least in Germany they are still used, but more frequently we are using kinase inhibitors or PD-1 inhibitors, so death cell receptors and things like this. So more specific structures which influence the immune system and help the body to fight for the cancer. We stop the cancer grow, increase the immune system, response, and thereby the normal response is getting. I'm pretty sure that almost all of us, we do have some cancer cells in our body at the moment. Yeah? But they are fought by the immune system. Good health conditions, good eating, sports, things like this. Not only drugs.
Thank you so much, sir. Your all sessions were very informative. My question is, sir, what are the different challenges in multi-targeting drug discovery? Because it may lead to the side effects along with the off-target side effects also.
The multiple targeting is that you must know all of the targets, you must know all of the structure-activity relationship, and you must all know the off-targets, which are normally combined. And here what we are using, all of our targets are already described as drugs. So we have a quite good knowledge what these drugs are doing and what they are not doing, or what side effects they have. So we really go into literature before we are starting here, and then we check all of the different aspects before we start such a project, if it's useful or not. Sometimes we are not sure, then we start it, but when we are sure that they are not really working together, then we do not make anything like this. And thereby, for example, we have also combined histamine H3 receptor with adenosine H2A and A3 receptor, which are also known for Parkinson's disease, and they were quite effective for both receptors, or even 3 receptors. They were very useful compounds, were all 3 receptors in nanomolar concentration range, based on our MAO inhibitors in this way. But when we tested them on Parkinson, they were ineffective. Later on, we detected with our screening that these compounds had some activity on dopamine receptors, some antagonist activity on dopamine receptors, and thereby we were not able to eliminate the antidopaminergic activity, and that was our failure with these kind of drug development. So sleepiness and so on was okay, but Parkinson's disease was not really addressed. So even that, we do make a lot of failures in this way. We learn from this, and that's what we all should do. Failures are not really the problem. We have to learn from the failure and getting, with improved knowledge, into better design. That's what I just can recommend.
Thank you, sir.
Hello, sir. In DNA barcoding, Salix term, what it use?
Pardon, once more?
DNA barcoding, for example, mRNA, it transfer the message, then Salix, what it works?
Yeah. You mean the RNA transferation, or what do you mean? I do not understand the question exactly.
So DNA structures we are identifying, so lots of barcode we are using.
Yes.
For example, here we are using particular functional group for drug synthesis. Then Salix term, what it works over there. Previous lecture we seen that. Okay.
Can you translate?
Yeah, so he was asking about Select. So that is actually protein folding, how it is remembering the things and those.
Okay, how protein is folding this. The protein folding is mostly physicochemical properties. And these physicochemical properties, what explained yesterday or in part, or the day before, in which way the partial positive and partial negative effects go together, make some hydrogen bonding and so on. In fact, this is not only for the protein, but mostly for some helper proteins, these chaperones. And these chaperones, they help this folding because they are binding to this, include this folding, and then release this structure. There are different chaperones like heat shock proteins and so on. They are well known in the different structures. They are confirming, or they are helping that the proteins are not freely fluid in all of the area, that they are orienting in some pathway. Mostly they are orienting to a good healthy condition, but you see with Creutzfeldt-Jakob syndrome or some other prion diseases that they have chaperones with some wrong folding, and then this wrong folding is addition, and then it's getting into diseases form. So normally it's nice and good and something to have. Sometimes it goes wrong. Yeah, but you need mostly some other elements. What is, maybe I may also add here, not to be too explicit, but also the osmotic factor is really important with the structure. So how many ions do you have in your solution? And do you have sodium or potassium, or do you have calcium or magnesium? This influences the structure, and then maybe in some cases you get different structures. So even the other elements which are in your buffer have strong influence on your protein folding, which is quite often underestimated. Yeah?
Any other questions from? Please ask more questions. This is the last lecture. Yeah, please, yes.
Hello, sir. Sir, if we have discovered any new plant species which has suppose antibacterial properties, but we don't know from starting.
Yeah.
So how can we predict this plant has these properties or not? Or there is any method?
Yes. The drug likeness properties you can easily determine by lipophilicity, by the physicochemical characterization of these compounds, and you have the antibacterial activity of your compound, because that was the reason you selected this compound, and thereby you can on relatively short term, you can calculate the drug likeness and drug likeness possibility. The main problem here with the antibiotic activity is that you are killing your bacteria, and that's your measurement. So you do not have the target in this way, and thereby you do not know in which way your compound is interacting with your target. You only see the end effect of your compound. And that makes it difficult to calculate, because maybe you have an intracellular target, yeah? Then you must calculate in which way your compound is penetrating the membrane, and only then it's active in the bacteria. Or you have a membrane target, then it does not matter really. And this is then important for drug optimization, if it's needed to penetrate through the cell membrane, or if it's just on the membrane to interact. And thereby the good knowledge of the target, to my mind, is in most cases really essential. Just killing cells is nice to have, but not enough. And at the end, you must show that your target is not any human target. That's not existing in humans, and that there is no interaction with this structural element. And it's also the case that at the end you must also show that maybe your bacteria is doing some metabolism on your compound, and this metabolite doing the toxic effects. Can you exclude that this happens or not? That's the problem, because you make some incubation. Incubation is mostly a few hours, and then you make and during this time there could be some metabolic pathways, and the responsible toxic compound is maybe one of the metabolites you're performing. That's difficult.
Hello, sir.
Yeah.
I have a question. You said you develop a drug that works on narcolepsy, symptoms, excessive sleepiness. Is there any other use of that drugs, like for night workers, or you said military personals?
Yes. There are some clinical trials in which way, for example, fatigue symptomatic can be treated. So where you are really exhausted and you cannot stand up really, and then with the high doses of pitolisant, it was quite effective that you are treating your fatigue symptomatic. And this fatigue is often connected to post-traumatic stress syndrome and things like this. So there are other possibilities you can achieve. I must say that at our university, we are obliged not to be connected to any military research in this way. So thereby, I cannot give any information on this, if there is something done or not done. We are not doing anything in this way, and I have not read anything in this way. But from a theoretical aspect, it's clear. And I must say that during, I think, First or Second World War, the pilots, they were taking large doses of caffeine and amphetamines just to stay awake, and they got addicted to this at a late stage. And this is something where you can stay alert and get not addicted for a long term, but I have no clue really.
Professor Stark, what is your take on traditional medicines? Multiple molecules, multiple targets. So how do you look at the research which is being done in this area?
I'm a big fan of traditional medicine in different ways. There are each country, each nation, each area has its own traditional medicine chemistry. In most cases, they are giving excellent ideas for new compounds. In many cases, they are not really the compounds which are really the best. And what should be observed with traditional medicine chemistry is to find any active ingredient. That is really, to my point, we are believing that not drinking tea or not the preparation of this, so we are not working on the homeopathic element in this way, and you know from your own Ayurveda medicine, there are some things which are more active than others, and some things need some prescription, where others are really active all the way and so on. And when you are having this acting all the way, then you can be pretty sure that there is something inside which is helpful. The main problem is that they are mostly plant-based structures in this way, and the quality, the maintaining of the quality is very difficult in this way, and thereby you do not know if you have more or less in one or the other structure when you start these different elements. And to my mind, here's also, if you have one active ingredient, then in many cases, if you have some sugar elements and some lipids and so on, they are increasing their lipophilicity, they are increasing their extraction behavior, they are increasing some additional properties in this way, and thereby it's not only one compound, but one compound in addition to some other mixtures are quite important in many aspects. And that's, to my mind, the main difficulty, that you at the best, you can detect and determine your active compound. Yeah, that would be the best always. And then makes an isolation of the compound, and then maybe we synthesize or derivative this compound, and that would be the most optimum. Because by that way, you're not depending on the surrounding, on the glucose structure, on if you have taken this in January or in February or in May, what is really the best month to take this? This is just by traditional, without science, is not really useful in this way. And thereby, my account goes that you determine the active ingredient, and then you have some possibilities. In Germany, we have the rules that when you have some plant-based structural elements, which can be prescribed for medicine, you have to determine at least one active ingredient in this way. Yeah? And this active ingredient, this then is standardized. So when you have some tablets or some liquids, when you buy these tablets or these liquids, they always have the same account of this standard material in this. By that way, you have some standardization. They are still made of the plant, so they are not really in this way, but different plant materials put them together to maintain this at a similar quality. This means we look for standardization of this medicine. We still keep this standardized traditional medicine in-house, because we see the benefit, also price benefit and things like this, but there must be also a quality assurance in this way.
Yeah. There is a similar rule in India also. Yeah. In the category of phytopharmaceuticals, those products must be standardized all the time. So that means we still are recognizing surprising uses of these traditional medicines.
Yes, there are always some surprises and things like this, and I'm pretty sure that in maybe 1/10 or maybe 1/3 of the so-called traditional standardized medicine, we have not the real ingredient in this way. Maybe it's a glycuronate or something like this. There could be other possibilities, but it's not really sure. We are sure that they are active biological compounds inside, and they are for clinical evidence, and with this I could only support this. And at the end, it's always at the help for the patient. That's what is always be the most important thing. And there, I even sometimes think, if you have some blue placebo which helps the patient, it's okay if it helps the patient, you can take a blue or red placebo. Yeah, so that's not the case. It's the only problem if everybody had to pay for it. That's something else we can discuss in this way. But nevertheless, the benefit for the patient should be the first interest in everything.
Any questions? Sir, I have one question. First of all, thank you for sharing your wonderful research work and thought-provoking lectures with us. And I have one question like multi-targeting drug design, how does it differ from drug repurposing?
How does the platform?
Drug repurposing.
Yes. Oh, on the one hand or the other, this stick together, because when you look on the side effects of many drugs, they're not connected to their original target, they are directed to some side targets. Yeah? Sometimes they are beneficial, sometimes they are not beneficial. And then this repurposing means that we take the side effect, and this side effect may be useful for another disease. So that could be connected to, in many cases, it's connected to multiple targeting. And the more compound you give, so the larger amount you give, the larger effect on other targets you really have. We have seen this with the CYP interaction and so on, but nevertheless, this could be really connected to each other. But for repurposing, it's really a good knowledge on the compound and on the effect of the compound. And effect is really not only the therapeutic effect, the whole effect it has with the patient. Yeah? So there are some compounds which have some effect on blood pressure. Yeah? They have some effect on hair growth also. Yeah? Then be aware in which way they have some effect on hair growth. Yeah? My problem, maybe.
Yes, thank you, sir.
So if there is no more questions, please join me in thanking with a big round of applause to Professor Stark for his wonderful sessions and with a very effective 5 days lecturing over here. And we should welcome him again because it's his first visit to India. I guess he also enjoyed and reciprocating to you as well to have a similar kind of response. Okay. So with that, I'll close these particular sessions, and after that, we have some time before we start the valedictory. That time we'll be conducting the exam. Okay. So that the link will be coming to your offline as well as online that WhatsApp group, and you can just go for it and get it done in half an hour. So that's it from me. Thank you. Thank you very much.